Hello everyone. I want to go over a quick review on chapter 7 basically, which was solving equations using power series. A part of this chapter, by the way, chapter 7 was also Euler equations, but that is actually didn't have anything to do with power series, at least the part that we did. And so that already I reviewed in the previous review lecture on second order equations. So for the power series the technique is rather simple, and so we're looking for a power series solution. And what does that mean? So let's go right away to an example. So we have a linear differential equation. I just take here one is 0, and we also have initial conditions always is 2 and y prime minus 3 is negative 2. So the first thing is that the initial conditions determine the center. If they don't mention the center, then you have to find it from the initial conditions, because you always have the initial conditions at the center. So this means that the center here is minus 3. But be careful, that means that we're going to look as a power series in x minus minus 3, so x plus 3. So we are looking for a power series of this form. Okay, so this is the solution that we're looking for. And so there are two things I will ask is, first of all, find a recursive relation among these coefficients, an. This always exists because we are ordinary points. Yes, I should mention that. So this is we only do ordinary points, and this means these are points where the factor in front of y double prime does not vanish. So, and in negative 3, this is not the case. Okay. Now this does have repercussions nonetheless. This factor here. So this would be minus 4, right? What is the problem with minus 4 is that in minus 4 the function, the solutions will be ill-defined. I'm not going to say too much about it, but in particular, it is a kind of we most likely. I'm saying most likely because we only touching the top of the iceberg here, but it gives a restriction and as how far my radius of convergence can work. Namely, it's always the radius of convergence from the center to the nearest root. Well, there's only one root here, so to negative 4. So we know that the radius of convergence is most likely just to be 1 here, which means in terms of series is not very big. But that's not our concern, so I'm just mentioning that because I don't want you to calculate in that. The second thing I want you to calculate is a couple of initial values here. I say in this case I'll do up to A5. I might, depending a bit on the series, ask you different up to a different degree. Okay, and so how do we work then? Well, the technique is straightforward, right? We gonna plug in y prime, so we have to calculate y prime, which is this is all standard calculations that we do many times. So x plus 3 n minus n minus 3 n minus 1 here n minus 2. Now before this is important though. Before I plug this in now in here, I have to write this. So I should perhaps okay. I write it here. So step 1. Let me write it. Center at minus 3, meaning all the coefficients here, all these polynomials, these are linear, so we're easy, but they could be, of course, quadratic. I think that's the worst we ever did. Have to be written in terms of x plus 3. And these are not polynomials in terms of x plus 3. So this means what we need to do here is we write x as x plus 3 minus 3 and then plug it in each of these coefficients. So we get 4 plus x, x plus 4. I don't know why they keep writing it in this order. I find this. So x plus 4, that becomes x plus 3 plus 1. Okay, let me write it this way. Y double prime minus, now we have 4 plus 2x, so 4 plus 2x becomes 4 times 4 plus 2, sorry, let me do this carefully because you have to be very careful here, don't go too fast, because 4 plus 2 x plus 3 minus 3. That is 4 plus 2 times x plus 3. Remember, this x plus 3 is now a unit. It's like it's an atom. You cannot split it up. And then we have 2 times minus 2, that's minus 6. So we see that this is equal to 2 times x plus 3 minus 2 y prime. And then the last one was 6 plus x. That is plus x plus 3 plus 3. That is easy, right? So I don't do this in my head. Equals 0. And now we have, what we did is center it at negative 3. So in other words, write it as polynomials. Write as polynomials in x plus 3. That's what I mean with that sentence. So step 2 is now plug in. And only do here. Do this first. Otherwise, you're not going to find your recursion relations. So we get x plus 3 plus 1 times summation n minus 1 a n x plus 3 to the power n minus 2 minus 2x plus 3 minus 2 summation n a n x plus 3 to the power n minus 1 plus x plus 3 plus 3 times summation a n x to the plus 3 to the power n. Okay, and this is equal to 0. So we multiply out summation n minus 1 a n x plus 3 to the power n minus 1 plus summation n minus 1 a n x plus 3 to the power n minus 2 minus summation 2 n a n x plus 3 to the power n. That's the first one, right? This one will give me minus summation 2 n a n x plus 3 to the n minus 1. The power doesn't change here. And then finally plus summation a n x plus 3 to the n plus 1 plus summation 3 a n x plus 3 to the n. And that's equal to 0. Step 2, or step 3, shift all to powers of x plus 3 to the x minus c to the power n. So there's a lot of shifts that have to happen here. So this one we have to do the shift n goes to n plus 1. So we get summation n plus 1 times n times a n plus 1 x plus 3 to the power n. That is now correct, it's shifted correctly. The next one I have to shift by n, which goes to n plus 2. So we get summation n plus 2, n plus 1, a n plus 2. Don't forget to do that index as well, right? And then we get x plus 3, n plus 2 minus 2, so double checking, yes, that works. The next one, I don't need to do anything. It's nice to need to just copy now. This one I do. I have to do the n to n plus 1 again. So that is minus summation 2 n. Oh, I set shift and I didn't do it. So 2, what is it? N plus 1, a n plus 1, x plus 3 to the power n plus 1 plus n. Okay, that one. Oh, that one here, and perhaps I'll do it in different color. I have to shift down. So n to n minus 1. And that is where we have to be a little bit careful, because this affects also the lower bound. So now n minus 1 is going from 0 to infinity. I didn't write this everywhere else because the shifts do make the summation start from negative numbers, but that cannot be, so we just ignore those. But here we cannot do this, we cannot ignore this. So this is the complication that comes in this general case when we shift down. So here we get a n minus 1, x plus 3 to the power n, okay? And the last one is locally already the way we want it, so we don't need to do anything. So we have our coefficient, so the coefficient of x plus 3 to the n, let's write now out what we have. And we know that you have to be 0, right? So 0, well, I'll write the 0 at the end. That is n plus 1 times n, a n plus 1. Now, okay, sorry. Yeah, sorry, I have to, let's do it in order. So the first one is, so this summation here, let's look at this. This means that n, sorry, I'm pointing this one, that n is equal to n. It starts from n, okay? So I'm going to rewrite this here. So step 4, let me call it step 4 already. Write down the lower terms. What I mean here is the ones that are not everywhere in every summation. So the ones that are not in every summation. When they're in every summation, then we can all put them together. But here if n is 0, this is one of the values where there could be more than one. But in this case, there's only one because everything starts from 0 except for this one. Okay, but suppose if this would start from 2, then we would have to do n0 and n1 separately. Okay, write down, perhaps I'll write it here separately. So in this case, for n equals 0, we get 2 times 1 times a1. No, sorry, I'm looking at the wrong. Sorry. Here, I plug in n equals 0. No, there's no term here. Here we do get a term. We get 2 times 1 times a2. Here we don't. The next one we don't get a term because of the n. The next one we do get a term, minus 2 times 1 times a1. This one we don't take because it's not there, and then finally this one we get plus 3a0 is 0. Now, of course, what this must be, otherwise we're in trouble, right? If we have one index, one one coefficient that we don't know yet. Remember, these initial conditions, the reason is that we have centered here is so that this would be a0 and so that this would be a1. That's the reason why we center here at -3, so that we have exactly these two coefficients. So we know what these two are, but we don't know what the next one is. So we have 2a2 is equal to 2a1 minus 3 times a0, so we see that a2 is equal to a1 minus 3 halves a0. And now we have the values. The values are 2 and -2. A0 is, so that is -2 minus 3 halves times 2, so that is -5. Okay, so this one we have to calculate separately always. But now if n is bigger than 0, so this is step 5. This is the general coefficient. Then we can just copy all of them. So we get n plus 1 times n, an plus 1, plus n plus 2, n plus 1, an plus 2, minus 2n an, minus 2n plus 1 an plus 1, plus an minus 1, plus 3an, and all this is equal to 0. So step 6, I'm breaking down now. So solve for highest index. So what is the highest index here? Well, we have an n plus 1, an n plus 2, n plus 1, n minus 1, and n. So this is the highest index. So I'm going to solve for that. So get n plus 2, n plus 1, an plus 2, and I'm bringing the other guys to the other side. Okay. Now there are some combinations. So let's see, an plus 1. What we get, but be careful, we bring to the other side. So if this becomes, it becomes a minus n squared minus n, I'm expanding that, and this becomes with a plus sign, plus 2n plus 2, okay? There are also ans, that would be plus an. This one comes with a positive sign because I bring it to the other side, right? And then this one goes with a negative sign, so I get that. And then finally, we have this guy here that is minus an minus 1. Did I have now everything? Yes, I have everything, right? Okay. So what we get is an plus 2 is equal to, let's write down what we have here, on top an plus 1. We have a minus n square, so minus n square plus n plus 2. That's, yeah, plus an 2n minus 3 minus an minus 1, and all this divided by n plus 2 over n plus 1. And this is what I mean with the recursion relation. This tells you for n bigger than 0, so n1, 2, and so onwards, we get this formula. You might say, well, what about a2? Well, a2 we have already, right? Here we have a2. So the next one we calculate, so step 6 now, I guess, is start plugging in values for n, starting from the first allowable one. So if I plug in n is 1, I get a3, and so a3 is then equal to a2 minus 1 plus 1 plus 2 plus a1 2 minus 3 minus a0 divided by 3 times 2. Okay, so let's see, a2 was negative 5, so we get negative 5, and then we get times 2. This is minus 1, this is minus 1, and then a1 is negative 2, so that is actually plus 2. Minus a0 is minus 2, and that over 6, so we get minus 10 over 6, or minus 5 over 3, if you want. And so n is 2, I'm actually only going to do these two, because this is now just plugging in, right? So a4 is now, we plug, but remember, but what I mean plugging in is always in this recursion relation, right? So now we plug in n equals 2, so we get an a3 here, we get a minus 4 plus 2 plus 2, oh, that's actually 0, plus a2, 4 minus 3, minus a2 minus 1 is 1, yeah, divided by, now in the bottom we have a 4 times 3. So this is actually 0 as we noticed, so we have actually, this is minus a2, which was negative 5, right? Or was it 5? a2 was negative 5. Minus a1, so it was plus 2 over 12, plus 2. So this is 12 over 12, no, sorry, 7 over 12, 7 twelfths, okay? And so on. Let me not work out the details. Okay, so these are several steps, and they're important. You have to do them in right order. And I remind you, the very first one is very important to do this, is to write everything in the right center, including not just, of course, your power series, but also the polynomials that occur here. And then you expand, you do the shifts. When you shift down, something happens. Namely, your endpoint becomes not 0, but is higher, depending on how you shift it. Which again has an implication, namely that if you run down the general coefficients, you can only do that from starting from the ones that are all that they all have in common. Okay, but that might be, in this case is only 1, but suppose sometimes it could be that this starts from 2 and this started from 1. That means that both 0 and 1 would have to be treated separately, and only from n equals 2 onwards they all appear, and we can write down the general coefficient which we did here, and that's the recursion relation. These are initial parts of the recursion relation. They're not technically recursion relation. This is recursion relation. Okay, all right. So it's really not so difficult, this one. It's just a matter of keeping very good bookkeeping of everything, and I'm not saying that I solved this completely correctly, because I might have screwed up a minus sign or something here or there, but be very, very careful.